with Michael and Rebecca. If LDA were not good, why we discuss them? So at least we get a sense of what's going on with LDA, and so we'll talk about other stuff. I would recommend you guys to. I'm not saying LDA is bad, but there's something other options we have. So before we do that, we have to discuss the limitation of keyword search. So because you understand the limitation of keyword search, you will see what's the advantage of machine learning and other stuff. So let's look at this very simple example, or naive simple example. So you see, we use the vector to represent the many person. So we use a frequency. So many person in this case, many appears one, person appears one. Just in case this document, so the vector is 1, 1. And in this case, many didn't appear, so it will be 0, 1. So you get the cosine of these two pretty high. But you look at this case, so many persons, 1, 1. I lemmatized them. Lemmatized means to go back to original form. So and then so here we use people instead of person. So because it's frequency based, so there's no frequency, there's no occurrence of person. So it will be 0, 0 in this case. I like I said, I ran naive. We don't do this in a normal calculation. I just simplify the example just to illustrate this stuff. But the logic is the same, but we don't exactly do like this. So the similarity over here is 0, but to human, it's not case, right? The many person and the people, if you look at similarity, this should be exactly the same. The cosine should be very high. So that's the problem with frequent based. Frequent based only counts on the frequency of the single word, and then it means the meaning of the people. So if we know the meaning of the people, we don't have this problem, right? We don't have that problem. So how to do that? How to do that? This go back to earlier Michael asked. Can we train computer to understand the meaning of people? Can we do that? So I ask you guys. You know what's the meaning of the people? So Hugo, what's the meaning of people? He told me people is us, right? We are people. But can you let computer to know what's the meaning of people? Can we train them? Can we do that?
Yes. So we can use like the labeling words to train the machine to understand.
Exactly. Right. Exactly. So can you explain a little bit more? Brainstorm this, yeah.
Yeah. I mean, you can ask machine, you can let that machine to read some text information. So the machine will identify the most frequently used words around the people, and then the machine can guess what people mean or what person mean. Maybe you can create a vector for person, create a vector for people, and then you can analyze the cosine similarity between these two vectors, and the machine will find the people is actually the same as person.
Very good, very good. The logic is totally good, totally good. That's actually what we did in the paper, and we're discussing today. So yeah. So, but let me just briefly give you guys example. I think sometimes let's forget about all this optimization, gradient descent. Let's just go to example to see what's going on. So let's say this sentence: earnings represents cash flow, which helps future investment. So what embedding? So earlier I was thinking, what was word embedding? This is word embedding. So what do we do is we mark this word. We cross cash flow. We cross it. And then we use the surrounding word to predict what would be the word here. So that's what we do in the word embedding. So we build a new network, not we. It's already done. Okay, I just use it. We just use it. I will sometimes say we. I mean, it's not me. It's our scholars. Our scholars. So what they do is we mark this cash flow, and then we use the surrounding word to predict the cash flow until we reach the high accuracy of we can predict the cash flow. So what's the output of this model? The output is the model is you will see that you can use the surrounding keywords, the surrounding words to represent the meaning of the cash flow. So for example, you see here there are the earnings, the investment, blah blah blah. So the intuition here is sometimes when we talk, we always say redundant things sometimes, language. Sometimes we say the stuff which are similar meaning. So what the machine learning do is not any words which, so basically not any words close to the cash flow represent the meaning of the cash flow. So let's say which help has nothing to do with cash flow, right? But the investment earnings has something to do with cash flow. So the model training is we can get the meaningful words into a vector to represent the meaning of the cash flow. So you will have a vector here which we take out all these nonsense words and we use the relevant words into the vector, and then that training process is called word embedding. And the way we train it is just use the surrounding word to predict the cash flow. Once you're able to predict, you will have output of the vector. The vector will be the relevant words which represent the meaning of the cash flow. So for example, the cash flow here will be represented earnings and investment, blah, blah, blah. So, okay, so this is a naive version of explaining it, but it's not exactly what we do, okay? I use this example as explaining the logic, but in really coding, that's not what we do. But what I said is logically right. Okay, the flow is right, the intuition is right. But in reality, what we have is a vector, which is numerical vector, which represents the meaning of the cash flow. Okay, and the vector, this is a parameter you can define yourself. It can be 100 vector, 50 or 20, whatever. This is a parameter you put into the word embedding. So word embedding, the only parameter you can set up is just the dimension of the vectors. So if you use 100, and then you will have a 100 dimension vector to represent the meaning of the cash flow. If you put 50, it will be 50 dimensional vector to represent the meaning of the cash flow. Okay, so the intuition here is right. We use the surrounding word to represent the meaning of the cash flow, but when we do the really package, this is the numerical number. Everything is numerical here, but the numerical number here actually can be mapped into this kind of words. But the only difficulty is we have to use so many clustering principal component. It's not a one-to-one mapping. So each numerical number here may map into different words. So it's not like earnings mapping to this number, investment mapping to this. You don't know. You just can't go back. You just don't go back. But you will know that this 100 dimension vector represent the surrounding relevant words around cash flow. That part is for sure. We just don't have the one-to-one mapping from each dimension to this dimension. But so that's what we have. So let's go back to this example again. So for person, you will have 100 dimensional semantic vectors. So people, you have 100 semantic vectors. So in this case, these vectors is trained using the words surrounding them, and also we take out the irrelevant one. So if you look at the similarity of these two, what do we have? High or low? You guys think? Very high, right? Because the surrounding word around the person should be highly correlated with surrounding word of people. And we already take out this irrelevant. So in this case, the earlier problem will not be a problem anymore because you have a semantic vector to represent the meaning of the person. So let's go back to the question I asked. Humans know the meaning of the people. How to that machine to know the meaning of the people? So that's the answer here. We use the vector to represent the meaning of the people using the model, using the training I just talking about. So typical example is, let me finish the example and we'll open to questions. So female plus king will be equal to queen. So how that happen? Because the surrounding word of female plus the surrounding of the king, very similar to surrounding word of the queen. That's what actually happen in the language. So that's why the two vectors add together will be the actor of the queen. So that's that. So once we have the vector to represent meaning of the word, you can do a lot of things, many things. We'll spend the whole semester to talk about what things we can do, but you can do many things. So this is step one. But then open to questions before I move on. Yeah. So there's more application for this. Okay, it's not just a dictionary. So another application is you guys see in the liability in the Wikipedia, the meaning, the surrounding word is like a burden, stuff, like you are my liability. It's like bad words, right? So But in our financial context, the surrounding world is cash, debt. It's about money. It's about liability. It's about debt. It's not bad. It's just borrowing. So you can see that if you train a liability using Wikipedia, you will get a semantic vector, right? You will train a liability using your 10K annual report conference score, you will get another semantic vector. The two vectors are not the same. Not the same because the meaning are different. So what's the implication of that? Implication is you can get domain-specific meaning of each word. So basically, you can get the liability in the medical domain, you can get a liability in the financial domain, you can get a liability in other domains. So you can get a domain-specific meaning of that. So that's another use of this word vector. So that's why Tim McDonald published a paper 2013 or 2011, I forgot. Finance PhD, 2011, 2013. The McDonald. 11. Okay. Yes, that's 11. Yes. So what they do is they said, so their whole paper point is we shouldn't use sentiment from the Harvard dictionary because Harvard dictionary is social emotion. We should use the sentiment using the financial dictionary. We use the annual report. So that's the whole point of the Tim McDonald's paper. So they use human to do that. So there's human reading the 10K and get the finance related positive, finance related negative. So if we do that paper right now, we can do that using this methodology. Instead of have a human reading them, we can train the stuff in the 10K or 8K. We can train the finance specific contents instead of have human reading them. So that's why Finbert, the Finbert is Google Bert finance version comes out. So okay, this is application 2, right? So you can get the domain-specific meaning of each word instead of just general words. Okay, so we can expand the dictionary. We can get a domain-specific dictionary. So another one is time series variation. So if you see, if you're a big fan of Shakespeare, so if you read some words broadcast in 200 years ago, it's about pharmacy. It's about not pharmacy. It's about agriculture. It's about broadcast seas. The surrounding world is seas and stuff. But right now, the broadcast, it's about CNN, blah, blah, blah. So you also can capture the time series variation of the meaning of the word. So if you use the Shakespeare's literature to train the words, it has certain meaning, but you have right now the online influencers language to train the words, you have another meaning. So you can also capture the meaning of the words, how they change over time. If that's something related to your research question, that's something you can do because some people do LDA. So the paper I was talking about, I think is Mark Land's paper. They do the topic of the 10K to see the topic MA, how the topic MA change over time. Like 20 years ago, it's about topic 10K is about blah blah blah. Current the 10K is about fair value, tangible. Before I forgot what they did, but they do the how the topics change in over time for the 10K report. It's something you can do. You can do that as well. If you believe that at each decade is different meaning, you use that decade to train this broadcast, and you get the meaning of that decade for that. And if you this decade broadcast another meaning, so you can slice your data into different time and train the words even different times. So this is another way you can apply that to the business setting and also sometimes like local dialogues, like sometimes people have different dialogues. You use the local dialogues, you can train them, you can understand the dialogues too. So these are the applications of this word embedding. So yeah, so you can see a lot of people using the Usenet to expand the dictionary. That's the number one application you see. But we can use many other stuff. I just encourage you guys to use other stuff too. So any questions before I move on? What's the problem with this approach? This approach also has a problem.
Sensitive to the corpus?
Corpus, but you can train the corpus, right? Liability. You can get the meaning of the liability.
You mean based on word level?
Yes.
Okay.
Yes. So, like Yajie says, this one is still have limitation because you only get the meaning of the cash flow, right? So let's say the whole sentence. This one is not working. Okay. So let's say this whole sentence. So you just get the meaning of the cash flow. But we want the meaning of the whole sentence. Like onions represent. It's a bad example. I just don't understand what does it mean. Onions represent the cash flow, which helps treating. Anyway, so this is a so we want to get the meaning of the whole sentence because it's not just isolated word. The onions related to the cash flow represent related to cash flow, and the help physical. So we want to have the whole sentence, the context. But this approach is still single word approach. It has context. Okay, you consider surrounding words. But the surrounding words is used to serve to get the meaning of the cash flow. But the sentence, for the sentence level, you only get the meaning of the cash flow. You don't get the other stuff. You don't get the relation between the words. That's problematic. Because language is so powerful. We cannot just say one word, and this is the meaning of cash flow. We want to get the meaning of the whole sentence. Everything. The syntax, context. That's one we want to get. So I want to give you guys an example. Another example. Okay, so let's look at the example here. I went to a bank to deposit a check. The bank here definitely is a bank, right? Okay. We walk around the river bank. So these two banks will share the same vector to represent their meaning. This is problematic, right? Because the bank, first bank and second bank it's completely different, right? Completely different. So what's the solution? The solution is we do not get the vector at the word level. If you just one vector to represent the bank, you always have this problem. So what we do is we will represent the whole sentence using a vector. So if you use the vector to represent the whole sentence, I went to the bank to deposit a check. If that whole sentence is a semantic vector, then the bank will have its own meaning in that sentence. And we walk around the river bank. If you use the whole vector to represent the whole sentence, then the bank will have its own meaning in that vector. So the solution here is instead of using a vector to represent one word, cross, we just every sentence will have a vector to get the meaning of the sentence. So that's the solution. Does it make sense? That's solution one. We have solution two. Let's talk about solution one first. Solution one and solution two. Solution one, that's what Rebecca was asking me. Google Bert. That's Google Bert. So the Google Bert. Let's go back to the earlier example. So we mark the cash flow to use the surrounding word to represent the cash flow. So what Google did is you mark 15% of the words, and then you use the surrounding words to predict the 15% of words. You get that. And then you mark another 15% of the sentence and use the surrounding word to predict that. And you mark another 15% of words. You do this multiple times, many times, until you can represent the whole meaning of the sentence. And can you imagine how long is the vector? Like here, I'm talking about 50 dimension vectors. But here, can you imagine how long is the vector to represent the whole sentence? 768. Yeah. So the vector will be 768 long vector to represent the meaning of the sentence by doing this. And this, what we call this is bidirectional. The reason is because we have to train the model from the left to the right and the right to left, because the order matters. Before you just get the cash flow, the order doesn't matter that much. But right now, the order matters because let's say same keywords. you flip the order, you have different meaning, right? So the training will be from the right to left to right, and you train multiple times, like 15% each time, until you get the meaning of the whole sentence. So again, the input of this Google Bert is the text. The output is 768 vector for each single sentence. For each single sentence, that's the output. So what do you do with the output? Okay, now you have a 768 dimension vector for each single sentence. How is that related to our research? Like, what do you do with that? How do you use that? This is pre-trained. Okay, Google spent 10 years to train. So it looks like easy, like from the word level to the sentence level, but it takes a long time to do that. It takes a long time to do that. But let's say you have the sentence level vector. What can you do with that?
You compare with other sentences.
Compare with the other sentence, right? Yeah, that's the easy way to apply, right? Easy to apply. So you can see that there's a paper. So let's say you compare annual report. You want to compare the annual report from 2011 to 2010. So how do you see the two documents are similar to each other? So before, what people do is get the frequency, right? You use the frequency of the words of the 2010 and the frequency of words of 2011, and you compare frequency. If the frequency is high, means they are similar. No, you're not. But there's a chance is that maybe everything's the same. They just change the order, right? They just use the similar words, blah blah blah. There's many ways the two documents may be similar or may be different. You just use the frequency may have some problem. But using this approach, you can identify what are the new sentences, what are the deleted sentences. So that level you cannot do using other stuff, right? You can, because at the sentence level you have each similarity. Like exactly go back to Rebecca's point, you have the sentence level, you compare the sentence of this one with the sentence of that one, and you can identify what are the new sentence and what are the sentence deleted. And use the new sentence, Lauren Cohan has a paper called Lazy Price. So what they do is they will show that if an annual report has some new information, investors just didn't get it because there's so much boilerplate in the annual report. And then once you add some new information, it's totally buried in the boilerplate. So they show that investors do not respond to the new information in the annual report in a timely way. The way they did is frequency-based. Frequency-based. So what I'm saying is, like Rebecca said, if you use this sentence-based, it's a much advanced one, but that will not guarantee a paper because normally, if the idea is done, you just use a higher technology to do that. Normally, people will don't like it. It have to be a new question, new stuff. What I'm saying is, if that idea hasn't been done, if no one has been done, if you compare the two annual report, what new information you can get a report, can investor respond? If that idea has not been done, you use this method will be better than using frequency similarity. But if the idea is done, you want to use the technology to show this is better. I feel it's very difficult. It's very difficult. But this one can help you to answer some questions like some other people couldn't answer before. So yeah. So this is one application, right? I'm going to use the. It's much more powerful than that. I will explain it. Much powerful than that. If you get a sentence level meaning, it's not just one word. You get a whole meaning of the sentence. So how do they do that? So how about I skip all this neural work? So it's 24 hours later neural work. So I give you guys a lot of videos, right? The video explain the architecture of neural work, and I give you guys how to train the parameters. I guess I will save my time on this. What's the structure of neural network, how we train them. That's just, you guys just watch the video and come to me if you have questions. I mean, you can, that's an efficient way to do. I think I give you guys so many videos sometimes. Yeah, so another disadvantage of this one is the 768 dimension vector, so no interpolation. You don't know what is that. Like each dimension is similar to the earlier stage. we don't know that, but we always can interpret that. So there's a way to interpret. So at this stage, if you guys really want to interpret, we can talk later on. Like I have some ways to interpret them ex post, like once you get everything, we can ex post interpret what kind of stuff they capture. So so interpretation is a problem for Google Box, so called Google Bert. So that's why I want to introduce another deep learning method also at the sentence level. That one is much easier to interpret, but less powerful than Google Bert. So so at the sentence level, I'll give you guys two options. One is Google Bert. Google Bert, you get a vector, and you get everything. It's powerful, but you don't know what capture, like what kind of keywords they capture, what syntax they capture. You don't know. So I will introduce another deep learning method, also sentence level. It's very easy to interpret, but not as powerful as this one, because that one captures limited feature of the syntax. This one captures everything about the syntax. But which one you use depends on research question. I want to present you the options and understand the idea. That one is also pre-trained. You don't need to train. You don't need to train. I always give you guys stuff you don't need to train. And later, if you want to train, we can train. We can talk about training later on. So
what is a good side of training a model ourselves compared with pre-trained?
one more time.